Space, the final frontier. This is the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. Its mission to explore the solar system, to seek out new observations and data, to boldly go where no podcast has gone before. And now the host of the Observer's Notebook, Tim Robertson.
Hi, everyone, and welcome to the Observer's Notebook, the official podcast of the Association of Lunar and Planetary Observers. Each episode, we share the latest discoveries, observing techniques, and stories from people who explore the moon, planets, comets, and beyond. Whether you're looking through a backyard telescope or leading professional research, we're all united under one sky. I'm Tim Robertson, your host, and thanks for being here. And if you usually listen to the podcast in your car or on your phone, did you know that you can watch it too? That's right. The Observer's Notebook is now available in video right here on the ALPO YouTube channel. And here's another interesting fact. Over 50% of the people listening or watching are not subscribed. So take a quick second, hit that subscribe button, and ring that bell so you don't miss any more episodes. It's free, and it really helps grow our channel. This show is made possible by support from you, our listeners. If you'd like to help keeping the Observer's Notebook going, check it out on our Patreon page at patreon.com/Observer's Notebook. For just $1 a month, you are supporting the show. For $5, you get early access to the podcast. For $10, you receive a copy of the Novice Observer's Handbook, and for $35 a month, you'll be listed as a producer of the podcast. And of course, to learn more about the ALPO, visit alpo-astronomy.org, where you can join the organization for as little as $22 a year. All right, let's get into episode 225 of the Observer's Notebook podcast. All right, I'd like to welcome everybody back to this special edition of the Observer's Notebook podcast. And today we have the ALPO Mars coordinator, Roger Venable, but we're not going to talk about Mars today. We're going to talk about IOTA. How you doing, Roger?
I'm doing fine. I'm well. Thank the Lord.
Good. Now, talk to me a little bit about the mission and the history of the International Occultation and Timing Association.
Well, now, this is not an area of my expertise, but it really began when David Dunham was young. He was, it was in the 1970s pretty much, and he was, I believe he was a grad student, and he developed programs because he was became an expert in celestial mechanics, and he developed programs to calculate orbits and so on. And his professional career has involved calculating orbits for spacecraft and so on, and dealing with the amount of acceleration they would have, not only from their engines, but from passing by celestial bodies. And so when we've had spacecraft boosted by encountering a planet or slowed down by encountering a planet en route to their destination, he's the kind of guy who would make those calculations. And so he worked with closely with NASA and other space agencies, and because he noticed that he knew about the limits of the accuracy of our knowledge of the position of the moon, the size of the moon. Mm-hmm. This was back before we'd measured the moon with the Lunar Reconnaissance Orbiter. It was long before that, And he found that we knew the accuracy of the stars much better than the accuracy of the moon, especially the moon's libration-related mountains and so on. And so he began studying and measuring and timing exactly when a star would disappear at the edge of the moon, and that would enable him to tell where the limb of the moon was at that moment.
Okay.
And then when it reappeared, he would have, another measure. And they accumulated a substantial body of information about the limb of the moon and made a lot of adjustments to what was the best information on that subject in those days, which was called the Watts charts. An astronomer named Watts um, uh, made high resolution images of the edge of the moon at various librations and so on, and various declinations as well, so that he had a good idea of the entire visible part of the moon with regard to the bumps and troughs on the edge. And he made photographs of those, and he published it in a form of Watts charts. And I've seen the original, one copy of the original of those. They were about 2 inches thick, and a big pile of papers, and it looked as though they were drawn by hand from the photographs. You see, but that's what they did, and it enabled them to know exact details about the size and location of the moon.
Wow, that's interesting. Now, how did you get involved? Because you're on the board, right? You're the vice president, I believe.
I'm current president.
Oh, current president. Okay.
I was vice president since 2013.
Okay.
And the president stepped down in as of January, and as vice president, the bylaws say the vice president will take over if the president is no longer available.
Lucky you.
And so, sometime around a few months ago, when we near the time of our annual meeting, the board determined to make me president.
Well, congratulations then. So how did you first become involved with the organization? What drew you?
I started doing measuring stars disappearing and reappearing at the moon, and particularly what we call grazing observations, where the star would be right at the top or bottom of the moon, the north or south edge of the moon. And that would give us multiple occultations. That is, the star would blink off, and when that mountain passed, as the moon moved through the sky so slowly, the mountain star would blink on again, and then it would blink off. And typically this might last a minute, sometimes longer, sometimes shorter, but we'd see multiple blinks on and off of the star, and that would give us a good idea about the mountains on the edge of the moon. And the really fun thing to do was have a number of people spaced 100 yards or 200 yards apart, and we would get multiple chords, and we would see the star blink on and off at different times at every station because of the slope of the mountains that it was occulting.
That's exciting to do.
It's a lot of fun.
Yeah.
I mean, you can question how really important science this is, but it was a heck of a lot of fun.
Yeah, because you're actually seeing something not static in space.
Yeah, that's right.
Actual motion.
That's
nice. That's nice. Have there been discoveries made over the years through occultations?
Oh, yeah, lots of them. Yeah. Now our efforts are we don't worry about the moon much. There are still sometimes people observing grazes and having fun with that, and also measuring timing stars just at the limb of the moon and so on. But the data acquired by the Lunar Reconnaissance Orbiter is so accurate. It's accurate to a foot or two, and that we just don't have a lot of science to gain from that now. Okay. And so if people observe lunar occultations, it's mostly for fun.
Okay.
And sometimes it's dramatic. I mean, if Antares disappears on the dark side of the moon, it's really dramatic, and you might get to see the companion, things like that.
That's true.
So, yeah.
Now, but occultations can take place other than with the moon, I think you were alluding to as well.
Well, yeah, we spend most of our time with asteroids.
Okay.
And so we have, we concentrate on this all the time. The type of discovery we're making is not only localizing the asteroid in space. Occultations are the most accurate means of exactly locating an asteroid in space. Now, some people may not know this because they think that, astrometry done, that is position measurement, we call astrometry, done by a large professional telescope will be more accurate, or by the Hubble telescope, but the fact is it's much less accurate than what we do. The reason is that the Gaia spacecraft has, and even before that, the Hipparcos spacecraft, localized the positions of the stars with such great accuracy that when a star blinks out now behind an asteroid, that is accurate sometime, well, to less than a milliarc second, better than a milliarc second.
Wow.
I mean, it's just really, really good, and so if now we have, say, a group of observers lined up across the path, lined up across the path of the asteroid. Each one will have a slightly different time of the disappearance and reappearance of the star, and we can thereby determine the size of the asteroid more accurately than any other means known, and we can determine the shape of the asteroid. Now, there's another method to determine the shape of an asteroid, and it's called light curve inversion. Now, the light curve of an asteroid is a measure of its brightness repeatedly, making many measurements over a period of a night or perhaps on multiple nights. And to get a full view with light curve inversion, you need also to see it at different declinations in the sky, different distances from the ecliptic, so that we can get a glimpse of the northern and southern differences in its brightness. When the north pole of the asteroid is exposed, it's slightly different brightness from when the south pole is exposed. And with the asteroid rotating, then we can see how the rotation affects the brightness. And with math that's too complex for me to understand, but the professionals, to be an astronomer, you got to be a mathematician, and the professionals have worked this out so that they can look at a light curve, put all the data into a computer program, and they get a three-dimensional view of the shape of the asteroid. And the one thing that light curve inversion cannot do is it can't detect negative things on the asteroid. So if there's a how can I say this? It can't differentiate a flat surface from a concave surface.
Okay. All right.
And so if a surface has a hole in it, it really can't detect that and differentiate it from a flat surface. I can show you one if you just let me share for a moment.
Yeah, go right ahead.
Let me just see if I can share my screen here. I've got the thing already showing. I hope it works. Let's see. Can you see my mouse?
Yep.
Okay. I recently set up 4 telescopes across the path of an asteroid.
Can you maximize that screen, that view?
Okay, let me see how I can do this. Maximize. I'm looking for the maximize. Let me try this. Does that help?
Yeah, that's better.
Okay. So these horizontal lines are the positions of my telescope across the asteroid. And so I got 4 occultations, and each one is of a slightly different length, and so it fits an ellipse. We calculate the ellipse that fits it best, and that tells us very well the size and shape of the asteroid at that moment. That is the size and shape of the projection of the asteroid onto the Earth's surface at that moment.
Right.
And this was sent to our friend Dave Harold in Australia, because he is the person with whom we file all these reports, and he uploads them to international databases and so on. And he pointed out to me that chord number 4, this one right across there, doesn't quite fit. And he's got the edge of the asteroid, the oval, aligned with the other 3 chords, and that one doesn't quite fit. and it's as though there's a flat surface or maybe even a little concave over here, and this looks a little bumpy. And he said, well, this looks like you just need to move number 4 about that far, and he calculated that that's one video frame. In other words, a video frame, a standard North American video frame, is 33 milliseconds in duration.
Huh.
And if he just shifted this asteroid by 33 milliseconds, he finds that it aligns really well. And so he wrote to me and said, this strongly suggests a time-base error. So I looked at it and darn, I had made a one-frame error in calculating the location, the timing of that one chord. And
wow.
So, now this is essentially the final version, and but this is the science we're doing.
Mm-hmm.
And of course, now if the asteroid is rotated differently,
mm-hmm.
we'll get a different profile. But that will enable us to determine the size of the light curve inversion that the photometrists are doing. Those who measure the brightness. Measuring the brightness doesn't tell you the size of the asteroid.
Right.
So they get a shape of the asteroid by having the computer process lots and lots of rotational light curves, but it doesn't tell them the size. But what we've done is we've told them the size, you see. And we actually can superimpose on this the shape model that they get. This is an oval here, but you can actually get a detailed shape model and superimpose it on our chords. And that's what I'm heavily involved in, basically. It's determining the shape of asteroid. By the way, IOTA persons have discovered approximately 20 moons of asteroids.
Really?
At this time, yeah.
Wow.
And the very first one to be was we required a lot of extensive documentation that it was real, but the very first one we just gave a big award to that had been funded by observers who contributed. It was a $4,000 award, a pretty healthy award. That's for nice. Being the first to discover an asteroidal moon. We called it the Madamo Award, which was named after Bill Merlin, who had himself as a professional astronomer who had discovered a number of asteroidal moons.
So you're not looking at light curves; you're looking at the blinking on and off of the asteroid.
Yeah.
Okay.
And it's much more accurate than it used to be. So I can drive on most of the ones I observe. I know where that shadow is going to be, and I can drive to the shadow, and we still have misses, but much of the time I can put the telescopes right in the path, and measure the size and shape of the asteroid.
Well, misses are part of the science as well. I mean, it's.
Yeah, that's right.
That's very good. So let me just explain this for our viewers. This is 4 different telescopes in different locations that you did this. Okay.
Right. So if the path is this is a small asteroid. I think the path was about 5 kilometers wide, the shadow path. And so these telescopes are roughly a kilometer apart, you see? Something like in that range anyway. Right. 3/4 of a kilometer or something. I don't know. You can do the calculations. But it was something like that. And some of them are really interesting because just to give you an example, there's an asteroid that you may have heard of called Phaethon, Phaethon. It's asteroid number 3200, and it is the parent asteroid of the Gemini meteors. Its actual classification now is not as a comet, but as an active asteroid. And the peculiar thing about it is that it moves, it's of named asteroids, it goes the closest to the sun. It goes, its closest approach to the sun is 0.14 astronomical units. And so it scoots in close to the sun, very elliptical orbit, crosses the orbits of Mercury, Venus, Earth, and Mars. And it is the parent of the Geminid meteor showers, and we don't think that it was ever a comet. What we really think is that its orbit has been extensively modified by the loss of material from its surface
Mm.
due to the actual heat-related shattering of rocks on its surface. So, as it gets really hot next to the sun.
Wow.
So, but with Phaethon, in January of this year, I set up 2 telescopes across its predicted path, and I got 2 hits. It was wonderful, and that means I localized the orbit with great accuracy. Now, in October of this year, I did it again. I set up 2 telescopes, and I had 2 misses.
Yeah.
And you say, well, what happened? Well, what happened is that the asteroid is continuously shedding dust and meteoroids, many of which impact Earth,
Mm-hmm.
in the Geminid meteor shower. And because of that, the asteroid's momentum in space is continually changing with each little particle that takes
Oh,
off from its surface. And
okay.
so its orbit is changing. And so I got 2 hits in January, and 9 months later, I got 2 misses with the same orbit prediction. So
Interesting.
this is really kind of cool,
Yeah.
And so,
You're seeing
but
just how
that's what I do.
dynamic this object is in its orbit.
Yeah, yeah.
That's wild.
So,
Huh. So, was that probably one of the most memorable occultations you've seen, or what are some of the
oh.
most memorable?
Well, that's difficult to know. Uh, there's an asteroid called Leona. It's asteroid number 319. Leona passed in front of the star Betelgeuse.
Hmm?
And I probably have this wrong. I believe it was in November of 2023 that it passed in front of Betelgeuse. And maybe it was some other year or month, but I think that's what it was. And Leona is a problem because what's called a slow rotator. So we don't have a good shape model.
Hmm.
And in about June of 2025, I set up 5 telescopes across its predicted path. Now it's a main belt asteroid, so it's not close to the sun. It's got a stable orbit, and I got 5 hits,
Oh
and there
my.
were about 4 other observers who also got single hits. So we had about something like 9 um, uh, chords across this asteroid, and we got a shape model from that,
Huh.
just a sort of projection of one position of the asteroid, one rotation phase of the asteroid. But, it's not enough to determine what phase it was at, what shape it was projecting onto Earth um, at the time of the Betelgeuse occultation. But there may be a time when we've had enough occultations by that asteroid to enable detailed uh, study of its shape that will enable diffraction studies to be done with that shape uh, uh, projected back to the time of its passage in front of Betelgeuse, so that we will get a better view of not only the size of Betelgeuse, but its regularity. That is it round? We
Hmm.
don't know if Betelgeuse is round. You see what I
Yeah,
mean?
yeah.
I mean, it's so big that it can have
Before it blows up, we got to
projections
find
from
out.
its
Yeah.
surface and so on. Yeah, and that kind of thing.
Yeah.
And does Betelgeuse have big sunspots? Well, there's some information about this already in the
Hmm.
professional literature, but the occultation of Betelgeuse, uh, if we can get this oddly shaped asteroid to cooperate with multiple occultations, we'll get a good shape, and we can project it back to the time of that occultation, and hopefully learn something about Betelgeuse, you see.
Hmm. Interesting. So, if someone wants to get involved with occultation timing, what equipment would you recommend?
Well, um, you can do it with any size telescope, but the smaller the telescope, the more restricted you are in the number of stars that you can see in that telescope. You need to video or make the equivalent of a video at a fast rate. Now, video used to just mean any movie, but nowadays it mostly refers to classic video. We call it NTSC in North America, as you know. And that's what's projected on your television screen, your old-fashioned television screen. And modern televisions don't do that anymore. They're all digital. But old analog video is still used. I use analog video cameras a lot. I also use digital cameras. And you need to have a frame rate on the order of 30 frames a second, or that's a 33 millisecond frame.
Okay.
And that's because you're trying to see this star blink off with accurate timing. And if you have a 1 second exposure and the duration of the occultation is half a second, you have not timed it very well.
That's
see?
True.
And you want to just make it accurate. Sometimes we use higher rates. I've used a hundredths of a second. In fact, I've experimented on one asteroid. I used 1,000th of a second.
Oh my goodness!
For an occultation by Apophis years ago, and and of course the noise in the video is then high because a very short frame rate is going to have a high noise, but still, I obtained useful data.
Now, when you use that faster frame rate, does the star still blink out, or does it gradually dim?
Yeah, let me say that typically on a 33 millisecond exposure that we see with standard analog video, 33 milliseconds, you get one frame of intermediate brightness. And that doesn't mean that the asteroid is half as bright during that frame. It means that it blinked out during that frame. So that frame has intermediate brightness because, say, the asteroid was visible for the first half of the exposure, but not for the second half.
Got it.
And so the brightness appeared to diminish. And it's the same with reappearance. You'll have one frame of intermediate brightness. And you can interpolate the brightness in that intermediate frame to further accurize your timing measurement, you see? You can say, well, that was about a third of that frame was exposed before it blinked out because it only lost a third of its brightness as we image that frame. See? So, we know how to handle that stuff.
Yeah.
Go ahead.
Yeah, with the new technology in cameras, CMOS and CCD cameras, and the GPS technology that we have now too, how has it transformed what IOTA is doing?
There are a variety of adaptations to new methods. And for example, when I use a digital camera, let me say first that we have what we call video time inserters that we can use with standard video. And what this does is a device that gets the signal from the camera within a millisecond after the frame is exposed, and it puts a timestamp on it. And that timestamp it has a GPS antenna, and it puts the GPS timestamp on it, and that timestamp is accurate to a millisecond. And that's about the limit of what we can do with NTSC standard video, at about a millisecond accuracy, But with in other words, that's a theoretical limit, and most of our error is related to the noise in the video, and that makes it less accurate than that. So, it's not uncommon for me to have an error estimate of, say, 5 milliseconds, and it's probably more common for me to have an error estimate of 20 milliseconds or somewhere in that range. So just so you get that idea. With digital, we don't have the same type of time inserter. That is, we can't send the digital signal from the camera into the computer or something and time stamp it with extreme accuracy. And what we usually use for that is a flashing device. Now, the onset of a flash from an LED is, for our purposes, instantaneous. It takes less than a millisecond from the time that current is applied to an LED to the time it's at full brightness. And so we have the LED in front of the telescope, and when it gets a current controlled by GPS, accurate to a millisecond, the whole field of view turns brighter because we're shining an LED right at the front of the telescope, see?
Okay.
And so we put that brief flash into our videos that we make with digital cameras. That's how I do it. And
Okay.
there are some applications on iPhones where you can hold up your iPhone and it'll make a pulse per second flash and things like that. I don't like that method because the iPhone causes a lot of obstruction of your aperture, and I just have a little LED in mine. Okay. So that's how I do it with digital camera.
That sure beats the old days of a tape recorder and the naval timing being recorded
it used
and a
to be
little
verbal.
clicker. Yeah. Well, I had a little clicker.
That's right.
Yeah.
I used to have a handheld tape recorder.
Yep.
And I would have WWV playing in the background, and I would just, when something disappeared, I would say off as quickly as I could, and when it came back, I'd say on, and I judged my delay as my personal equation, something less than a second. I think, with experience, I got down to less than half a second, believe it or not.
Yeah.
But the point is that it was gross compared to what we do now. I mean, it was a substantial fraction of a second was the limitation of accuracy, whereas now, with a really good exposure, it's not unusual at all to get down to a 25th of a second, somewhere in there.
Yeah. Do you see new tools or methods out there in the future, like AI automation or things like that could shape the future of occultation timing?
Well, I should think that ought to be a very good question, but I don't have a good answer.
Okay.
So, as I think about it, the struggle we have is to really become skilled with the methods we're using. And it's not that it's always hard. It's often fairly easy to do what we do, but there are mistakes that are made, and they're not that uncommon.
Mm-hmm.
And so it's just it's like the time when I timed something and I was off by a frame, and so I showed you that diagram, and it gave us a better view of the shape of the asteroid and so on. So I really don't have a good answer how AI could help us. I just don't know what to say about that. AI will be involved with orbital computations,
right.
I'm sure, and particularly in cases like Phaethon, which is having its orbit shift due to the loss of mass from its surface. So, I just don't know what more to say about that, except that I expect these things to evolve.
Okay. Yeah, IOTA's had a reputation of being very collaborative between professional and amateur astronomers. How important is that dynamic?
Well, it's fundamental, really. Now we use the Gaia spacecraft's star position measurements for virtually all of our predictions, and the professionals have just by observing asteroids and measuring their positions, have gotten substantial accuracy in asteroid orbits, much better than it was 50 years ago, really much better. And then the radar that's been developed that can do radar positioning is more accurate than most other methods. Not as accurate as occultations, but still more accurate than optical observations with large telescopes. And so when an asteroid comes close enough to Earth to be within radar range, you might call, now this is not an Amana system, a radar range, but when a range of bouncing radar images off the asteroid, they can measure its location and distance with extreme accuracy. I'd say with extreme accuracy, but it's still not as good as occultation. So we'll take their data and then we'll spread out across the path and hope to localize it even further, you see.
Okay. So does IOTA have a training program for new observers that want to get involved?
I don't know that we have a specific training program right now, but it's most people just start setting up one telescope, and they probably restrict themselves to asteroidal shadow paths. By a shadow, there's no visible shadow. We're talking about a star blinking out, but the dimensions and so on, the physical aspect of it is sort of as though it were a shadow.
Right.
And that when that goes over your home, you can make a video of the star. And if you have a good timing method, either a flash device for digital or a video time inserter for, video time inserter for video and flash device for digital, then you can get good scientific data that way, just from a single cord. So we just explain that to people, and we can tell them what equipment to get, and the website will tell them as well. And so I think there are roughly 1,000 observers worldwide who are more or less accurate in this, more or less active in this endeavor.
1,000. That's quite a bit. It's and most of them probably travel to see occultations.
I think that most do not. A lot of them do, because they're interested in it, and it's fun, But most probably just wait for one to come over their house.
Okay, all right.
And but I travel, and to get 4 cords set up, there's 4 telescopes set up in the path. I travel. I do that more than once a month.
Oh, wow.
I think this year I've done probably average about 2 a month.
Okay.
And I look for events, occultation events that will enable me to drive to them and to set up a bunch of telescopes. In other words, I have a bunch of telescopes, and I try to concentrate on those events that are in the middle of the night, because that gives me time to set up a bunch of telescopes after dark, spaced across the path, and to pick those telescopes up before sunrise.
So when you say
all this,
when you say a bunch of telescopes, what type of telescopes are you talking about?
Well, I most of my telescopes are catadioptric. I have a bunch of Maxitovs and a bunch of Schmidt-Cassegrains. I also have a couple of large Newtonians, but I don't carry them around.
We can't do that anymore, can we?
I'm getting old. I don't know about you, Tim.
No, I hear you. I hear you, Matty. I've gone from the 5-inch refractor down to 6-inch Maksutov, and that's a lot easier to carry.
Yeah.
So are there upcoming occultations that IOTA is especially excited about?
Yeah, I think I have an interest in potentially hazardous asteroids. Phaethon is one, the one I mentioned, and that's why Earth is in the path of the rocks it has shed. It causes the Geminid meteors, because its orbit passes so close to Earth. I've forgotten what the mean intraorbital distance is. It's something like 0.05 right now, 0.05 astronomical units. But the problem is that its orbit is evolving. So it could evolve such that it becomes closer to Earth. And that's the kind of thing we're studying with occultations. That is, we want to know how that orbit's evolving. You see, that's exactly what we're doing. And there are a list of something like 30 asteroids with diameters greater than 400 meters that are potentially hazardous. The reason I draw the line at 400 meters is not that the others aren't hazardous. I think a 100-meter asteroid would be something like the Tunguska incident. You know what I mean? It would destroy a large city. Or if it hit in the ocean, it might cause a tsunami and this kind of thing.
Right.
But the point is that occultations get increasingly difficult with smaller asteroid size. And I've had success with asteroids down to 400 meters in size.
Oh.
And so that's why I arbitrarily limit myself to attempting asteroids of 400 meters or larger.
Okay.
Because that's the smallest I've been able to see.
All right. Going back to Pro-Am collaborations, did IOTA play a role in the NASA's New Horizon mission to Pluto?
As a matter of fact, it did after the encounter with Pluto. In fact, I made 2 trips to Argentina to participate in the research on what's now called Arrokoth. I don't know the number of it. It used to be called MU-69, but now it's named Arrokoth. And you know how these things are. It's named after some important false deity of yesteryear. Or something like that. Anyway, so I was the first trip down there we missed, but it turns out that one of the we had all misses. I think our first trip to Argentina we had and a trip to South Africa at the same time for the same night. You know, when I passed in front of the star, and we were really disappointed. But it turns out that there were 2 runs with the Airborne Infrared Observatory, SOFIA, Airborne Infrared Observatory, and they discovered that they got a very brief hit on one of those flights.
Oh.
And the second time we went down, we got, I'm going to try to remember, I think we got 5, if I remember right, we got about 5 or 6 chords across Arrokoth. And that really localized its position. I mean, just, you know, pinpoint for something far out beyond Pluto, which is really amazing.
That's incredible.
So the New Horizons spacecraft flew by it and adjusted its own flight path, you know, and posted past it and got really cool images. So, and as you know, you probably remember Arrokoth, although it's not a binary, it looks like it's a contact binary, you know, like and of course it's rotating. So it's a very interesting object in that regard.
Wow. So as the president of IOTA, where do you see it heading in the next 5 to 10 years?
Oh, goodness. I see it as unpredictable. I'm not quite the dreamer who can, you know, visualize the future and head toward what's good. I'm not like that. I just try to have fun observing. So I see myself as basically an observer.
Okay.
You know, I'm also a Mars coordinator.
Right.
I've almost given up observing Mars. So many other people are making observations, and their skies are better than mine, and so on. But I'm still interested in Mars. But back in the 70s, you know, I had a couple drawings of Mars published in Sky and Telescope, and I had a couple of reports of seeing its moon. I saw Phobos on one side of Mars, and then hours later on the other side of Mars in the same night.
Oh my.
Things like that, you know. So, I mean, I used to be interested in stuff like that, but I'm still interested, but I'm concentrating on saving the planet instead.
That's a good goal. I appreciate that. If there was someone that wants to get involved with IOTA, what would you recommend as best way to start contributing?
Okay, let me just say that we have a website called occultations.org. There's a good bit of information. It'll lead you to the software, for example, that will help you process your observation. But most people, I think, when they become involved, have questions. And we have a website that's very active. my guess is we have 20 messages a day on that website. And and a lot of people are asking about how to do something or why didn't my equipment work and things like that. So, it's a good place to get advice from people who have a lot of experience,
Okay.
And I should say nobody's an expert because we all make mistakes.
There you go.
But we have a lot of experience and often we can help. And that's on Groups.io. So if you go to groups.io, search for occultations, and you will then find the occultations website.
Okay.
Yeah, listserv. It's a listserv.
Okay.
And like other things on, it's like the old Yahoo groups. We have a files section, we have an images section. The files section will have a lot of stuff that you can explore and advice and so on. And a lot of messages. And anybody who joins that group would be more than welcome to ask questions and discuss equipment and so on.
Fantastic. I'll put a link to both those in the show notes as well, so people can easily get there from there. All right.
Yeah.
All right. You have anything else you'd like to share with our audience today?
I guess that. Oh, let me just brag a little bit.
Oh, go for it.
I figured. I think it was yesterday, in anticipation of this podcast, I said, I ought to be able to tell them how many asteroids, how many times I've done this. And I've set up a telescope for approximately 240 asteroidal events. And on those, I have averaged almost exactly 2 hits per event. That is, when I started out, I was doing 1 chord. Now I'm doing 4 chords, and I have my share of misses.
Mm-hmm.
And so I think that 2 hits per event is not a bad lifetime average.
No.
And I've set up a total of 800 some setting up a telescope 800 times on 236 events or 240 events, somewhere in there. And I have about a 1 out of 4 complete miss rate. And that is, I get nothing. Mm-hmm. Things like that. But I still have 480 asteroidal occultations that I've reported.
Now, has it increased since you've retired?
Actually, I think it has a little bit, but not, but less than you might imagine.
Yeah, so, you were a physician, right?
Yeah. I practiced medicine for 43 years.
Fantastic. Yeah. All right. Well, Roger, I want to thank you for coming on the podcast today. This is very informative. I'm sure our listeners and viewers have enjoyed it. And we will talk to you soon about Mars on the podcast.
Sounds good to me.
All right. You take care.
See you later.
All right. Well, that's going to wrap it up for this episode of the Observer's Notebook podcast. A big thank you to Roger Venable for coming on and joining us today and sharing his insights to the International Occultation Timing Association. If you enjoyed the episode, please take a moment and give us a thumbs up and subscribe and share the podcast. It really helps us reach more listeners. New episodes of the Observer's Notebook are released every few weeks, and you can find us on iTunes, Spotify, and the ALPO YouTube channel. If you'd like to help support the podcast, you can do so through Patreon. For as little as a few dollars a month, up to $35 a month, will you receive exclusive benefits, including 1-year membership to the ALPO and producer credits on the podcast. You'll find out the links of Patreon and the ALPO website in the show notes. And I really want to thank Steve Seidentop and Michael Moyer for their continuous support as producers of the podcast. And you can reach me directly anytime via email at tim.robertson@alpo-astronomy.org. That's all for now. Thanks for watching. You can join the Association of Lunar and Planetary Observers today. It's just this easy. You can become a valuable member of this International Lunar and Planetary Astronomy Organization, founded in 1947 by Walter H. Haas. It's based upon the structure of the British Astronomical Association. You can join various lunar and planetary observing sections, contribute to our massive archive of observations. You'll have access to our extensive lunar and planetary gallery of over 20,000 photos and observations of the sun, the moon, comets, meteors, and the planets. You'll receive our quarterly publication, the Journal of the Association of Lunar and Planetary Observers. You have the ability to join the ALPO training program, which will teach you the finer points of making planetary observations. You can attend our annual virtual conference, and you'll have access to the Observer's Notebook podcast. Membership begins at only $22 a year. The way to find us, just go to your Google and type in ALPO Astronomy, and you'll see this prompt come up. There's our association with our website, alpo-astronomy.org, and you'll come to our homepage. If you look at the top of the homepage, it says Join ALPO. Click on that, and you'll come to the sign-up screen. It gives you the information on the organization, and there's two ways to join. You can join by mail, where you'll download a membership form, or you can pay online using PayPal. This is the PayPal processing page. You just fill out a few information lines, and then you're given the chance to click PayPal and join the association. Welcome to the ALPO.